This third tutorial introduces OpenGL Mathematics, GLM, which is a C++ library based on the OpenGL shading language, GLSL. Note that compiling GLM for linking with at compile time isn't necessary because GLM is a header-only library. To download GLM, search Google for GLM Maths and then click on the OpenGL Mathematics listing under the address github.com. Once the page is loaded, click on the latest link and then download the GLM zip file listed under Assets. After having unzipped GLM, open the parent folder, within which you'll find just a single folder named GLM. Open that folder and you'll see several folders and files, one of which is also named GLM, which is the folder that needs copying to your own includes folder. So now let's look at the code. There are 3 additional includes to those used so far in the first 2 tutorials. glm.hpp includes all GLM's core functionality. The matrix transformation extension is used to create various matrices within our program, and then we use those matrices to perform different matrix transformations. The type pointer extension is used to acquire the address of each of those matrices that we create. The only new OpenGL function call in the first part of our program is glEnable glDepthTest, which is required for drawing in 3D. For all the meshes being drawn, the Z values of all the vertices and their corresponding interpolated values are compared against one another. Any mesh face that exists behind any other face fails the depth test and is therefore not drawn. For the vertex data, notice that we now have an array of cube indices, which is because we are now using glDrawElements instead of glDrawArrays. The difference is that by using glDrawElements, it allows each vertex to be used multiple times, which can be more economical. Quote from Kronos: "Being able to store the vertex attributes for that vertex only once is very economical, as a vertex's attribute data is generally around 32 bytes, while indices are usually 2 to 4 bytes in size." End of quote. For example, a cube consists of 6 sides, each which consists of 2 triangles, which totals 12 triangles and therefore 36 vertices, and so if we weren't using glDrawElements, the total number of bytes for our cube would then become 36 times 32, which equals 1152 bytes. It then follows that by using indices, we can reduce the number of vertices from 36 to 8, as we're doing here, which is a saving of 28 times 32, which equals 896 bytes, but only at the expense of 36 indices which typically average about 3 bytes each, which totals 108 bytes. Therefore the final saving then becomes 896 minus 108, which equals 788 bytes, which is a 68% reduction of our original 1152 bytes. Notice that each of the cube's 6 faces use 2 vertices twice, which is where the saving comes from. However, it can also be a disadvantage to reduce the number of vertices to this extent. For example, trying to apply the same texture image to all 6 faces doesn't work, because you would need to assign more than one texture coordinate to any given vertex. Also notice that there is an additional buffer object that we create, which is the glElement array buffer. The next part of the program declares and sets up the majority of our transformation matrices. The key things to notice are the glm lookat view matrix and its position and target parameters, which typically change within the main loop as the program or game is running, and also its third parameter camera up, but which doesn't change. The glm perspective projection matrix, which takes 4 arguments: the field of view, the screen aspect ratio, and how close and far away into the 3D scene is to be captured for rendering. And finally, that in addition to our own transformation matrices, we are using glm's rotation, translation and scaling transformation matrices to transform our own matrices that we have created. Next we consider uniforms, which are global variables that are stored in the shader program object, which means that we can pass various data types to the shaders before each rendering draw call within the main loop on the CPU side. A uniform variable can be accessed in any given shader stage simply by declaring the uniform name within a particular shader stage, such as in the Vertex shader and/or Fragment shader, and the uniform's value does not change within any given shader stage from one shader invocation to the next, and so whatever value is passed in from the CPU side before the draw call becomes the value available for all the invocations of all the individual shader stages. To transfer uniform variable values to the shaders, we first call glGetUniformLocation, which returns a handle to the uniform as an unsigned integer. The first argument is our shader program ID, and the second argument is the name of the uniform as it appears in the shader. We then pass the handle along with various other parameters to glUniform to transfer the values. For example, glUniform1i model number location, 3 tells OpenGL that we are passing one integer, being the value 3, to the uniform variable referred to by the model number location handle. Another example is glUniform matrix 4fv view matrix location, 1, GL false, GLM value point of view, which tells OpenGL that we're passing only one matrix, that we don't want the matrix to be transposed, and the pointer address value of where this matrix is stored on the CPU side. The first part of the main loop declares the float variables that are used to randomise the rotation speed and rotation axis of all the smaller cubes, as they each orbit around their own unique orbit. We also declare two GLM vector 3 arrays, one for each cube's orbit and one for each cube's rotation. The second part of the main loop calculates each individual cube's orbit by calling the updateOrbit function. First, the initial position offset is translated back to centre, XYZ 000. It's then rotated by some relatively small amount and then finally translated back along what has now become a slightly altered path back to the orbit perimeter. Additionally, the updateNormal vector function is called for each individual cube, which calculates the rotational direction of the arbitrarily chosen right-pointing face, which is being used in a similar manner to how normal vectors are used in lighting calculations. The third part of the main loop, after having calculated all the cube orbits and normal vector directions, then transfers both arrays to the fragment shader to be used in the lighting calculations. Finally, glClearColor is called to clear the screen, and then one at a time each cube is drawn by calling the drawCube function. Now let's look at the Vertex shader. The first out vector 3 variable passes the APOS Vertex attribute position values unchanged to the fragment shader, which are then used within the fragment shader, interpolated, to set the initial colour of the individual cubes. The second out vector 3 variable also passes the APOS position values to the fragment shader, but only after first being transformed by the transformation matrices. These values are also used as interpolated within the fragment shader, but for the lighting effects as opposed to setting the initial colour. In addition to receiving the view and projection matrices as created and passed from the CPU side, we also receive the 4 transformation matrices that are used to control each individual cube's position and rotation. We use the model number uniform to identify which type of cube is being drawn. The 3 if statements are then used to select the correct transformation matrix uniform based on the model number uniform's value. It's worth noting the right to left multiplication order which comes into play for model number type 3, whereby the scaling only matrix takes effect first, then the rotation only matrix, and then finally the translation rotation combined matrix. And finally, let's look at the fragment shader. First, the initial colour values are set based on the interpolated vertex position values. Next, the light shining direction of each individual cube is calculated by subtracting the transform vertex positions of the cube currently being rendered, which are passed in from the vertex shader, from each individual spinning cube's orbit position. These subtractions give us the line of sight light direction from the centre of each of the 6 spinning cubes to the interpolated vertex positions of whichever cube is currently being rasterised for the given draw call on the CPU side. For each cube, we then compare its light shining direction to its own rotational direction, and then use that angular difference to calculate the specular light intensity that it shines onto the cube being rendered for this particular draw call. We then select 6 different colours and multiply them with the 6 individual specular intensities, and then add them together to produce the combined specular lighting effect. And finally, the last part of our fragment shader takes advantage of each cube's centre being the origin from which its own light is emitted, and therefore allows us to control the dot size that the cube shines onto itself.